Okay, so this is where we stopped last time, blocking and unblocking, non-blocking assignments. Any questions, Anirudh? Any questions so far?
No.
Okay, just let me try to position this slightly differently. Okay, yes. So RTL modeling. What does RTL modeling does for us? It will help us describe the system at a higher level of abstraction. Higher level of abstraction compared to schematic design. So Verilog as a language allows us that higher level of abstraction compared to schematic design where we are focusing on gates and gate connectivity. Here we are describing the hardware using a language. Specify a set of concurrently active procedural blocks. So as we have seen, procedural blocks are basically always block and initial blocks in Verilog. Those are two kinds of procedural blocks in Verilog, and they help us develop digital circuits which execute concurrently or parallelly in nature because hardware is parallel in nature. So the language should allow us to build such hardware which is parallel execution in nature, which has that parallel execution requirements. So RTL modeling will help us do that. Using the procedural blocks, initial blocks, uh, which will help us to develop initial conditions. So we have seen that initial blocks can be used to initialize the hardware or to develop logic which can be executed on reset of your chip, PGA reset chip. So any reset logic or initial conditions as they are called can be developed using initial blocks. In test pictures or when you develop a test bench in Verilog, we can also generate test vectors with initial blocks. We'll see that when we see the test bench design, but test bench design in the test vectors of the test inputs, as we call them, are applied from the initial block rather than the always block. Then the always block can help us develop combinational or design combinational circuits or sequential circuits or also develop FSMs, finite state machines. So latches or flip-flops are part of sequential circuits. Always block can help us do or build any part of digital logic design. So that is something that always block will help us do. When you look at the procedural blocks, there can it can have multiple statements within the procedural block. For example, initial block can have one or more statements. Always block can have more than one or more statements. The initial inside the initial block or inside the always block, the execution is always sequential, one after another statement. Line number one, line number two, line number three. Same with always block. Line number one, line number two, line number three. Initial block, all the logic or various statements that are part of initial block will be executed only once on reset. So they'll execute once and then stop. Always block, on the other hand, will keep executing this logic based on the sensitivity list or the signal list as we call them. So it could be a sensitivity could have normal signals in them, could have clock edges sensitive to clock edges. So the always block has a sensitivity list which will trigger the always block. Any logic inside the always block will keep executing depending on the sensitivity list. But inside the always block is all sequential. Inside the initial block is all sequential. You can have more than one always block in your Verilog code. When you let's say there are three always block in your Verilog module. Inside the always block one, inside always block two, or inside always block three, it is all sequential. But always block one logic with respect to always block two logic with respect to always block three logic is concurrent execution or parallel execution. That's how you can develop parallel logic in Verilog. Let's say there is a chunk of logic which has and there is chunk number one, chunk number two. Chunk number one needs to go into always block number one. Chunk number two needs to go into always block number two. That's how logic can work parallel with respect to each other, because both always block will get executed parallel. Okay, so that is how parallel logic can be built using Verilog language, which is used for hardware description. And this kind of feature is not available in a programming language, at least not the normal ones. Now there is work going on parallel computing and other stuff, but it's a different problem to solve. Normal programming language doesn't allow you parallel execution in normal sense. So the language doesn't support it. It's actually the OS that supports it. So that's how parallel logic is executed. Any questions on this? Do you understand this? Because this is a very important concept.
No.
No questions?
No.
Yeah, okay. Can you note down these things, the small diagram in front of you, and just whatever I said in the small notes? Notes for yourself.
I'm done.
You done?
Okay.
Okay. So there are various things you can do with the RTL statements. There are various kinds of RTL statements, rather. There are procedural and RTL assignments. The assignments inside the procedural blocks, like out is equal to A plus B. This is one example. Then there are begin and end to create blocks of statements. So any always block or any initial block should have a begin and end. Normally, begin and end is required if you have more than one statement inside the always block or more than one statement inside the initial block. It's always a good practice since you're just starting out. It's always a good practice. By default, any initial block or any always block, you should have a begin and end. So that is how you group the various statements inside the always block or the initial block. Then there are certain conditional execution statements like if, else, if conditions. There are certain things called case statements. We'll see some examples of this. Like any language, we'll have for loops, we'll have while loops. There's something called forever loops. So forever loop is something that's used only in test bench for simulation purpose. Because in hardware there is nothing called forever. It works with respect to inputs. So forever loop is something that we use only for test bench or simulation purpose. And disable statements, we can disable a statement which is also something fancy, which is not part of the design. It is not synthesizable. It can be used for test bench purpose, but not for the design part of it. Let's look at some example. Now this is a module. So everything, if you remember, everything in Verilog works with respect to module. So if I just say module gadget end module, basically I'm not doing anything inside the module. It's a do nothing circuit. In this case, I have some input output ports declared. Module gadget ABC, out of which A and B are input ports, single bit, and C is the output port single bit end module. Though we have declared input output ports, still this module or this design is not doing anything. So it is still a circuit which is not doing anything, even though it has input output ports. IOs declared. Combinational circuit design. When you do combinational circuit design, combinational circuits are such that outputs are functions of inputs all the time. There is no memory involved. The current set of inputs and the logic that we have will decide the output. So the current set of inputs, the logic processes those inputs and the outputs are generated. And this keeps happening on a regular basis. We don't have any memory of the past history of inputs or past history of outputs. If the inputs are processed, the outputs are generated. Some examples of combination circuits are multiplexer, demultiplexer, encoder, decoder, priority encoder, adder, subtractor, etc. If you look at a multiplexer, now this if you see here, this is a gate level representation of a 2 is to 1 multiplexer. So how does a 2 is to 1 multiplexer work? There are two inputs, there is one select line. When the select line is high, one of the inputs goes to output. When the select line is low, the other input goes to the output. That's how a 2 is to 1 multiplexer will work. So it's represented at a gate level using this circuit, where I have two AND gates to input, one OR gate to input, one input. So I can build this 2 is to 1 multiplexer using a structural modeling technique. This what you see is a gate level or a structural technique, a structural method. Module mux 2 is to 1 out A B select, where out is single bit output, A, B and select, each of them is single bit input ports. I have declared a wire which are nets basically, data type nets. Simple wires called select underscore A1 B1. These are the wires. Select underscore is connecting the inverter output to the AND gate input. A1 and B1 are connecting the AND gate outputs to the OR gate inputs. So I instantiate this designs here, or this modules here, or these gates. I can instantiate here not I0. This is my I0 instance. Dot Y goes to the output goes to select underscore. Dot A, which is input, goes to select. So select is mapped to the inverter gate here. Then AND2 is instantiated twice. This gate. First instance is called I1, the second is called I2. Here we are using a shortcut method. So we do not want to use, technically speaking this works, but always use this correct method. Or this more elaborate method, which is what you should do going forward. So A1 of this is the output Y or the output of the AND gate is mapped to A1 signal. A is mapped, the second input is mapped to A input here. The other input of the AND gate is mapped to select underscore. Second AND gate is instantiated called I2. B1 is my output of the AND gate. Then this input goes to B, which is a primary input here. Then the other input goes to select, not inverted, but just a normal select, which is also the primary input. Then we have this final OR2 gate instantiated here. The instance label is I3. Y output goes to out, which is a primary output. First input goes to A1 net or wire. The second input is connected to B1 wire. N1. So I have created this 2 is to 1 multiplexer, which was represented using gates, has been modeled using structural modeling technique. So if I apply the appropriate inputs at A, B and select lines, I will get the outputs accordingly. For example, A is 0, let's assume that, and B is 1. So select goes here, and select is 1. So A is 0, B is 1, and select is 1. What should be the output in that? Can you tell me? A is 0, input A is 0, input B is 1, and input select is 1. Hello? Still there? Hello? Yeah.
Yeah, yeah.
Okay, I thought I lost you for a second. Okay, yeah, go ahead, please. Take your time. Let me know what is the output. So I'll repeat the inputs. A is 0, input A is 0, input B is 1, and input select is 1. What will be my output in that case?
1,
Output will be 1.
1.
Any other answer? And you have to justify the answer. So you have to tell me how you came across that answer. So we'll wait till Anirudh gives his answer and then you can give the explanation for that.
Okay.
It's one.
It's 1. Okay, so Ruth, can you go ahead and tell us how you came across this answer?
Just applying the gates. The first gate, the output for the first gate was 0, and then the second and 2 is 0 at I1, and then I2 is 1, and then applying I3.
Okay, so A is 0, B is 1, select is 1. When select is 1, when select is 1, B input will go through to the output. The A input AND gate will be 0. Output of A input AND gate will be 0. B input AND gate will be whatever B input is. And then OR will just solve them and give the output. So that is a gate level explanation. So what I would like you to going forward, what you should do is, this is a multiplexer, right? This is a 2:1 multiplexer, which is a combinational circuit. A combinational circuit. So how does a mux 2:1 work? If you draw a simple block diagram, let's see if I can draw. Okay, so I have. This is my A, this is my B, and this is my A input, this is my B input, this is my output. This is a multiplexer 2:1. So the way you should program your mind going forward is fine. We can deduce the gate operation and find out how the input passes to the output. But a mux 2:1, how it will work is, oh sorry, I forgot the select line. Right? So I need to have the select line also. Shield. So this is my A input, this is my B input, this is my select input. When select is 0, one of the input is going to pass to the output. When select is 1, the other input will pass to the output. In this case, select is 0. Uh, means in this case, if select was 0, the first input, normally the A input will go to the output. If select is 1, the second input, B, passes to the output. So that is how you should train your mind going forward. You can reduce this, that's not a problem. Multiplexer, combinational circuit, two inputs, one output, select line decides which one goes to the output. So it will be much quicker and easier for you to visualize that and put it in a Verilog code. Okay.
Yep.
Okay.
So same multiplexer. Earlier we saw this multiplexer design using structural modeling technique. If we do it using continuous assignments, how does it work out? Module mux 2 is to 1, out A, B, select are my ports. Out is single bit output port, A, B, and select is single bit input ports, each of them. Assign, I'm using a continuous assignment, which is a assign statement outside the always block. Assign out is equal to A and not select, or with B and select. End module. A and not select, B and select, you logically or them, you get the output. So this gates was converted to an equation that became my equation for the output. That's using a continuous assignment. Now the same mux 2 is to 1 if I want to model using RTL modeling or behavioral modeling as before. Module mux 2 is to 1. Out AB select. Same ports, same input output port declarations. There is a reg call out, which is the same name as the output port. Why? Because I'm going to assign this out or output port inside the always block. And the assignment rules for a register is for output, in case I'm going to assign directly to output, is if I'm going to assign a value to output inside the always block, then I need to have a register with the same name. Only then, since it's the same name, internally they will be connected. So if I assign it to some value to a register inside the always block, that goes to the output as well. But that's the assignment rule that I have to have a register with the same name. Reg call out. Then there is always block. Always at A or B or select. This is my sensitivity list or activation list. Any change in A input or B input or select input, this always block will be triggered. Begin the always block. If select equal to 1, tick B1. If select is 1, out gets B. Else out gets A input. End the always block, end module. So this is a behavioral method of designing a mux 2 is to 1 multiplex. Here if you see we are describing the behavior of a 2 is to 1 multiplexer. Check for select line. If select line is 1, output gets B input. Else, that means if select is 0, out gets A input. And always. So this is a structural method. This is using continuous assignment, or we also call it sometimes. You can see this is called data flow modeling in certain books. And this is behavioral description or behavioral modeling. Earlier this used to be called RTL modeling. But behavioral modeling is something that people refer to nowadays. So this is behavioral modeling. This could be called data flow modeling. This is structural modeling. Same design can be done using three methods here. Any questions?
No.
So before you note down this behavioral description, I would like to ask one question. Now, is this assignment that we have here, is it a blocking or a non-blocking assignment? I believe it should be only for you, Anirudh, because Root, you were not there for the last lecture. So Anirudh can maybe answer that. The current assignment you out register, is this is it a blocking assignment or a non-blocking assignment?
This is a non-blocking assignment
And why would that be?
because if because of the if statement, if the select line is one, then it's giving the output as B for the first cycle, and if it's not one, then it would be A.
Yeah, but we don't have any clocks here, right?
Sorry, this is a blocking assignment. It's just comparing the condition and giving out the output. It's not giving output one at a time.
So that's a blocking assignment.
Yeah.
Are you sure? Any change in the answer? How do we define blocking and non-blocking? And how is it represented also in Verilog?
Logging assignments, you expect it to give an output with zero delay, and non-blocking assignments, it operates in a clock cycle.
It's after the delta delay that it gets updated. So normally the end of the always block, so there is a delay involved.
Yeah.
So, and how is it represented using Verilog language? Syntax. How is it syntactically different?
Here it is, the output is dependent on the select line. Until and unless you configure the select line, you won't get the output.
Yeah, but syntax wise, how is it different? Syntax wise. So Verilog language representation. Is there any difference in the blocking and non-blocking assignments that from which you can also make out whether it's a blocking or a non-blocking assignment?
Uh, uh, yeah, the output is less than equal to,
Is
which states that it is non-blocking.
and if it's a blocking assignment,
It's just equal.
right? So when you say angle equal to, this is angle equal to. When it's angle equal to, it's a non-blocking assignment. When it's just equal to, like something like a regular assignment. If you do that, then it's a blocking assignment. Angle equal to non-blocking, regular equal to blocking assignment. Since this is angle equal to itself, we can say non-blocking assignment. Blocking and non-blocking assignments are more pronounced, or the effect is more pronounced in case of sequential circuits where flip-flops are involved, where clock is involved, right? In this case, we have a combinational circuit. Combinational circuits, technically speaking, it doesn't matter whether you are using blocking or non-blocking because combinational circuits, the definition of combinational circuit is output is a function of input. So output will get updated as per the input values and the logic obviously involved. In this case, the logic is if select is 1, out gets B. If select is 0, out gets A. So, but at the end of the day, we said that we would use non-blocking assignments for all design-related purpose, for all design-related Verilog description. So that is why we would use non-blocking assignments even in case of combinational circuits. And this by representation in Verilog also is a non-blocking assignment. Okay, so you can note down this example. So this will be one of your example designs that you can write a test bench for later on. You can only note down the behavioral description. You don't need the other two, data flow. If you want, you can note down, but you don't need it.
I'm done.
Okay, done.
One second. I'm done.
Okay. So this is an example of a 4 is to 1 multiplexer. Earlier we saw 2 is to 1 multiplexer. Module mux 4 is to 4 underscore 1. So the name of the module should always be synonymous with your design. This is my port list. Out, in 0, in 1, in 2, in 3, select. Out of which out is single bit output port. In 0, in 1, in 2, and in 3. Each of them is single bit input ports. Select is an input port 2 bits. We are using a continuous assign statement to build our 4 is to 1 multiplexer. Assign out is equal to select equal to 2 tick B00 question mark in 0 colon select equal to 2 tick B01 question mark in 1 10 question mark in 2 select is 11 question mark in 3. So the way this works is if select is 0, 2 tick, so this is pronounced as 2 tick B, a 2-bit binary number 00. Select is 00 in 0 input will go to output. Else, if select is 01, 2-bit binary number 01 in 1 input goes to output. Else, if select is 10 in 2 goes to output. Else, if select is 11 in 3 goes to output. Else, by default, there should always be a default in case of this conditional operator statement. 0 will go to output. 1 tick B0. So 1 bit value 0 will go down and more. So even though select is a 2-bit number, and a 2-bit number can only have these 4 combinations, right? 00, 01, 10, and 11. You should always have a default value defined as in this assignment. So this question mark and colon, if you remember, this is the conditional operator. So we are using a conditional operator along with the assign statement, continuous assign statement. Build this 4 is to 1 multiplexer. And how will a 4 is to 1 multiplexer work? Select, there are 4 inputs, so we need 2 select lines. Select lines is n number of lines. Input can have 2 raised to n number of inputs. So 2 select line can have 4 inputs, 2 raised to 2. Depending on the select line value, one of the 4 inputs will go to the output. That's how a 4 is to 1 multiplexer works in digital circuit. That is what is modeled using this assign statement or data flow modeling concept in Verilog. Any questions?
No.
Okay, so you can note down
No.
this example also. This will be another example you can try out. You can build a test bench for it later on.
I'm done.
Okay, done.
Give me one couple of minutes.
Okay. And note one more thing, select equal to two tick B. This is not, this is two equal to. So we are comparing the select signal or the input with a particular value. If it was single equal to, it would have been an assignment like this. Assign out equal to. So this is a comparator operator. This is a conditional operator. Okay. Uh, Now this was using the data flow modeling technique. This example is done using same mux 4:1 is done using a behavioral modeling technique. Module mux 4 is 4 underscore 1 out in select. This is my port list. Out is single bit output port. In is a 4-bit input port. Instead of single inputs, we have a 4-bit input port. Select is 2-bit input port. There is a reg call out which matches the same name as the output port because I'm going to assign that output port inside the always block. So due to the assignment rules, I have to declare a reg with the same name. Always at select or in. This is my sensitivity list. Any change in select input or any change in input will trigger my always block. Begin the always block. Inside the always block, I have a case statement. My case statement variable is select. That means and case statement variable is select. So depending on the select values, I can execute various statements. If select is to tick B00, if select is 00, out gets 0th bit of input or in signal. In is a 4-bit signal. So 0th bit of in goes to out if select is 00. Else if select is 01, out gets first bit of in signal. If select is 10, out gets second bit of in signal. If select is 11, out gets the third bit of in signal. In a case statement, there is a default case always, every time. In the default case, you should mention whatever the default values. In this case, out gets 0, 1 tick B0. End case, end the always block, end the module. So this is a behavioral description of a multiplexer using a case statement in this case. Okay, so any questions on this slide?
No.
No, okay. So if you want, you can note down this. Depends on you how, when you design, there are no restrictions. You can design using any method that you wish. It could be behavioral modeling, it could be data flow modeling, it could be structural modeling. Normally, nobody uses structural modeling for bigger designs. So normally you would end up using, most of the time you'll end up using behavioral modeling. So it's up to you which method you would like to use. Hello, Anirudh?
Yeah, I can hear you.
Now you can hear me? Okay.
Yeah.
Yeah, so this is a behavioral description of 4:1 mux. You can design your multiplexer or any circuit for that matter using any of these methods. Could be behavioral method, could be data flow method or structural method. So normally when you work on bigger designs, so these are smaller designs, so you can separate out the data flow using continuous assign, like what we did here. And this slide where we are using pure behavioral modeling. Normally, when you work on bigger designs, the behavioral modeling and the data flow modeling using continuous assign will be mixed. It will be a mixture of behavioral and data flow. That's why we don't call data flow modeling separately. It's all part of behavioral modeling. It's only that method, the behavioral method and the structural method, where you purely create a structure of the design. That is what you differentiate between. So you either will be using behavioral modeling, which where continuous assigned statements are part of your modeling technique, or you will use structural modeling, where you're going to instantiate the various gates or various components, do the interconnections, and create a purely structural model out of it. So ultimately, you will work on two methods: structural method and behavioral. Okay, so if you have done with this, we can go ahead. Next example.
I'm done.
Okay, you're done, Amir, or you still need time?
Yeah, 1 second. I'm done.
Okay. So next example is a decoder. So we have a 3:8 decoder with enable control, which is active low. Okay. So before we look at the Verilog example, can you tell me how a decoder works? In this case, a 3:8 decoder. How a digital circuit of a 3:8 decoder should work. You can assume active high signals here. So just to reduce the complication. So when I talk about a 3:8 decoder using digital logic, what are the inputs, what are the outputs, and how is the behavior of that circuit? See, Verilog is just a language, right? Verilog is just a language. Ultimately, you're designing digital circuits. So, digital circuits, if you know them, then you can write Verilog code for it relatively easily going forward. Language expertise can be developed. Yeah, sorry, go ahead.
Yeah, you have two inputs and eight outputs and three select lines.
Say that again. I know it was not clear. How many inputs? How many outputs?
You have two inputs,
Two
no,
inputs.
three inputs,
Okay.
uh, eight outputs, and three select lines.
Three inputs, three outputs, and three select lines. So select lines are inputs or outputs.
The select lines are inputs.
Okay. Why do you need a select line for that? Okay. Then how will it work? Let's say you have this inputs, three inputs, three select lines, and eight outputs, right? How will
Yeah.
the circuit work?
So since there are three select lines, we have 2 power 3, which is 8-bit output.
Since we have three select
8,
lines,
yeah, and yeah, that is what I think. So since we have like three select lines and 2 power 3, 2 to the power of 3 will give us the number of outputs, which is 8.
so you have three select lines. So how will I mean what I think the last part was not clear when you explain how the output is generated. The audio was not clear. So you have three select lines. How will it control the output?
So
Any other answer? Ruth, any other answer?
No.
Okay, so I'll explain. 3 is to 8 decoder. See, when you have a decoder, there are no select lines. Select lines are involved for multiplexer and demultiplexer. When you talk about encoder or decoder, there are no select lines. In this case, it's a decoder. So 3 is to 8 decoder. 3 inputs, 8 outputs. 3 inputs are binary inputs. 0 0 0 0 0 1 0 1 0. I mean, the possible combinations are binary combinations. 0 0 0 0 0 1. 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. These are the possible combination of inputs. When when inputs 3 inputs are 0 0 0, there are 8 possible outputs. Let's call them O0 to O7. Output 0 to output 7. When input is 0 0 0, O0, the zeroth output will go high. When input is 0 0 1, O1, which is the first output, will go high. When input is 0 1 0, the second output, O2, will go high. So on and so forth. When input is 1 1 1, when input combination is 1 1 1, O7, which is the last output, eighth output, will go high. That's how a decoder will work. There are no select lines for a decoder. Select lines are only involved for multiplexer and demultiplexer. If you have a demultiplexer instead of a decoder, the way it works is there is only one input. It's reverse of multiplexer. Multiplexer is many 2 raised to n inputs, one output, n number of select lines. You flip around inputs and outputs for demultiplexer. One input, 2 raised to n outputs, n number of select lines. With decoder, you have n number of inputs, 2 raised to n number of outputs. If inputs are 3, 2 raised to 3 is 8, you have 8 outputs. If inputs are 2, 2 raised to 2, there are possible 4 outputs. But there are no select lines. Okay? That's how a decoder should work. Now, since we know this, how do I design this using Verilog? Module decoder. Now, this case, you have to one more trick added to this is there are active low outputs. So instead of the output going high, the output will go low. That's how it will work. All the signals are reversed. It's active low means 1 is 0, 0 is 1. So that's how with the enable control which is active low, and the outputs are also active low. Module decoder, DEC out, enable bar, DEC in. So this is pronounced as enable bar, enable underscore. This underscore at the end itself tells me that it's active low signal. That's just a guideline that is followed in design work when you do design. If it is active low, you put an underscore at the end of the signal name or the input name. So anybody reading this will know that this is active low signal. These are my ports, out of which DEC out, DEC underscore out is output port 8 bits. So this output port is an 8-bit output port. Enable bar is a single bit output port. DEC underscore in, DEC in is the input port 3 bits. I have a reg called DEC out 8 bits, which is the same name as the output port, because I'm going to assign this register or assign this output rather inside the always block. So I need a register with the same name declared as the output. Always add enable bar or DEC in. This is my sensitivity list. Any change in enable bar signal input or DEC in input will trigger my always block. Begin the always block. If enable bar DEC out gets 8 tick B 11111111. If enable bar, so this is enable bar, this is an active low signal. In normal case, if enable was high, then output would have gone high. In this case, enable bar is going high, means enable is not enabled, it is disabled. Enable bar is going high means it's active low signal going high, so it is disabled. If it is disabled, output should be disabled, all the outputs. Since it is active low outputs, instead of 0, all outputs will be 1. I have 8 possible outputs. 8 tick B 11111111. This is LSB, this is MSB. Left hand side is MSB, which is O7, as we just discussed. Right hand side is LSB, which is O0. I can represent 8 bits in Verilog using underscore in between just to make it more readable. So this is allowed. in between underscore. 4 bits, we can have groupings of 4 bits. So if enable bar goes high, means enable is disabled, and the output is disabled. Since it is active low, instead of zeros, I will have outputs as 1, all 8 bits. Else, begin the else statement, because I have more than one statement inside the else block. So else block, this else section will also have a begin. Inside the else statement, there is a case statement, case dec in. So if else means now in this section my enable will be 0, enable bar will be 0. Enable bar is 0 means enable, the design is enabled. So I can start working my decoder logic here. Case dec in. If dec in is 3 tick B000. If dec in is 3 bit 0, dec out gets the 0th bit is output is activated. In this case active low, so it is 0. Rest of the outputs are deactivated, means ones. When dec in, decoder in is 001. The second bit output number 1 is activated. Activated active low means 0. Rest of the outputs are 1 deactivated. DEC in is 010. Second, the output is activated means 0. Rest of the outputs are 0 all the way to 111. When 11 DEC in decoder in is 111, my MSB output 7th bit, 7th output is activated. Rest of the outputs are deactivated. By default, there should be a default statement because we are in a case statement. By default, DEC out is disabled. All of the outputs are disabled. Since we have active low signals, all of them are 1. End the case statement, end the else block, end the always block, end module. This is how a 3:8 decoder with active low enable and active low outputs will work. Do you have any questions on this?
No.
No?
No.
You can note down this example. This will be another example you can write a test bench for and try out.
I'm done.
Done. Okay. Done, root. So if I would like to make one change in this Verilog, what will that be? There's something minor which is wrong in this Verilog. And if you can make one change in this, or you can find one mistake in this Verilog code, what will that be? Well, I'll ask two mistakes. And mistake, I mean, you can improve the Verilog design. You can make two changes there.
Can we reduce the default condition?
Say that again.
Can we reduce the default condition?
Can you remove, is it?
Yeah, reduce.
Which default condition? In the case statement?
Yeah,
No, that's part of case statement. You need a default there. In the case statement.
okay.
Fundamental mistake, correction, or improvement. Okay. Any guesses?
Semicolon after always.
Your voice is not clear, Anirudh. Can you speak up a little bit?
Yes, semicolon after always. Is that the error? We can use semicolon after always.
I'm still not able to hear you properly. Is there a way to put it in a chat, or can you talk a little slower? Because sound is not clear, very clear. Mm, no, I cannot see that. Right? There is no chat. Yeah, I did. Can you repeat the last part again, Anirudh? I didn't get you properly.
Yeah, semicolon after begin.
No. Sorry, yeah, no. That's not the one. No, we are not worried about semicolon. So one change I would do in this design is instead of blocking, I'll use non-blocking assignments. Right. This is intended to be a design. So I would try to change by default, use non-blocking in my design everywhere. So that's one thing I would do is change all the blocking assignments. And the rule with blocking non-blocking is if you use non-blocking once, you have to use non-blocking throughout the design. So I will change all the blocking assignments to non-blocking assignments. That is one thing that I would do to improve my Verilog coding. Though it's not going to make any change in my result, but still. Another change I would make is, as we just discussed, every now this if statement has only one. This if block has only one statement. Still, it's a good practice that every if else block or always block should have a begin and end. So after if there should be a begin, after this statement there should be an end. Then else, begin, all this stuff, end. So we can add a begin and end here just to make a habit of it. Those are two things we can make here, two improvements maybe to just for better practice right from the start. Apart from that, it's pretty much whatever is there we'll implement a 3 is to 8 decoder for us. Okay, so any other questions?
No.
Okay,
Why would you want to use non-blocking? Is there an advantage for using non-blocking assignment?
yeah, non-blocking assignment will actually it's more beneficial for sequential circuits, but we still use it for all the circuits. With a non-blocking
Okay.
assignment, now if this condition is true, this gets 111. This is blocking. Means DC out will get updated with this value immediately without any delay. Now, if I use a non-blocking here, which is angle equal to DC out non-blocking angle
Mhm.
equal to gets 111111. This will get updated at the end of the always block. We call it gets updated after a delta delay. That's how the terminology is. It gets updated this DC out at the end of the always block
Mhm.
after a delta delay. Why is that? And why is that beneficial? Is when you consider hardware design, whether you take a simple AND gate, if you take even a simple AND
Mhm.
gate, there will always be a non-zero delay from application of input to the time when the output changes. In case of an AND gate, it's a simple propagation delay,
Mhm.
right? So, but there is always a non-zero delay. That's how hardware works. There are delays involved.
Mhm.
The non-blocking assignment mimics the hardware design correctly at a simulation level.
Okay.
Even at why are you doing simulation and then going to synthesis and backend implementation? The simulation should also show you the same behavior as your hardware design should show you on the board when you're working on the board. So when you use non-blocking assignment, the simulation will show you that delay, which will be similar to what you'll get in actual hardware design. That's why you should use non-blocking assignments everywhere as far as design goes. Design means anything that
Okay.
gets implemented on a chip and finally on a board.
Mhm.
For designs, everywhere you use non-blocking. For test benches are only meant for simulation purpose. For test benches, you're free to use blocking assignments. No problem.
Okay.
Okay, so we will stop here today, and next class will be on Monday, same time.
Okay.
Okay, have a good one.
Sure.
Yeah,
Yeah.
Thanks, you too.
bye bye.